All right. So on Friday, we learned how to kind of combine the pH, pOH, all that stuff in with the ice tables that we learned the previous week. So there's kind of connecting the dots there. And that's what we're going to be doing for the next few weeks, honestly. So even after spring break, I think. Um, but it's very important to have these ideas up front before, I guess you have two more classes before your test. So let's see what you guys are doing. You're learning. Tomorrow is going to be more about ions, salts, and pH. So you're probably going to be learning about what happens when a weak acid or a weak base is in one of these ice tables. Um, or that's what we did on Friday. So tomorrow is going to be more stuff like that. And then Wednesday is kind of a almost only conceptual class where you're going to be talking about based on how we look at the structure of these acids or bases, how can we tell if it's strong or weak compared to something else? So I'll do a test review on Thursday for all that stuff. But for now, we can keep going with this stuff. So um, let's get right into it. We have one where it says the pOH of a 0.03 molarity solution of strontium hydroxide is blank. Real quick, what is strontium hydroxide?
Um, okay. It's something.
It's one of the strong bases. Yep. So we learned that for strong acids and strong bases, do we need to do an ice table? No, you can skip the ice table. It makes it very easy. But we still have to be careful. And this is a good example of a problem where you have to be careful. So spend a few minutes working on it, see if you can get the answer, and then I'll go over it up here. Did either of you get a POH for this one?
Um,
Okay, let's see. I got 1.22 for this one. So the step we have to be careful about is specifically when we're dealing with some of these strong bases, we can have a 2-to-1 mole ratio of hydroxide ions to strong base ions or molecules. So we have we can kind of draw the whole thing out if we want to be extra clear and do the whole multimole ratio. But in your head, you might get kind of quick at these and simply go, okay, I see strontium hydroxide. I know that's going to produce two hydroxide molecules for every one strontium hydroxide. So all I'm going to do is multiply the molarity of strontium hydroxide by 2. And that's what I did. And so once we have the molarity of OH minus ions or hydroxide ions, we can do the negative log of that to get pOH. And then the next part, I was asking what is pH? And so we're going to do 14 minus that to get pH. So 1.22 is pOH and 12.78 is the sorry, 1.22 is the pOH. I don't know if I said that the first time. And 12.78 is the pH. So again, we would expect this number to be very basic. So if you were doing this on a test and you see like strontium hydroxide and your pH is in the acidic range, that means that you did something wrong. You got to go back and try again. So that stuff's not too bad. Let's go on to weak acids though, or weak bases, how they behave. So we have a weak acid that has a hydronium ion concentration equal to 5.2 times 10 to the minus 4. I'm asking what is the pH? Hello. So this one, I kind of made it seem like we're going to do an ice table. This is a weirdly worded problem. Uh, this one, all we have to do again is do the minus log to get the pH. So um, it's because I said specifically we have a hydronium ion concentration equal to 5.2 times 10 to the minus 4. So if we're given the hydronium ion concentration, we can go straight through with doing the minus log of it. A more typical problem, and hopefully I have some of those later on, would be um, yeah, we'll talk more about this on number 4. Uh, that's where we only have like the concentration of our weak acid, and then we have to do a whole ice table to find the hydronium ion at equilibrium. But this one, it's real simple. We're doing minus log of 5.2 times 10 to the minus 4. So we're going to get a pH of 3.28 and then a pOH of 14 minus that. So let's see what that is. 10.72. So I won't spend a whole lot more time on that one. Not a great problem, but this next one is some stuff that is new. I think it was introduced to you guys late last week. Or maybe it was when you first started talking about pH, but it's important to know that the pH scale is a logarithmic scale. So that's a whole lot of stuff that I don't fully understand, but knowing these, if you can understand this part here, you know the basics of it, you're going to be good for the test. Um, and so basically on a logarithmic scale, every time you go up one value, it's a factor of 10. And so let's try this first one. I'm saying when pH goes from 5 to 2, by what factor does the hydronium ion concentration get impacted by? So first off, let's do only the first part. pH is going from 5 to 2. We're getting more or less acidic. More acidic. So would we expect hydronium ion concentration to be increasing or decreasing? Increasing, yeah. So we got that part done. So now we need to figure out what the factor it would be is. And again, it's always by factor of 10, each step you take. So going from 5 to 2, there's 3 numbers in between there. So the way you solve this one is 10 to the power of 3 is the factor that it's being impacted by. So we know that that's 1,000. So the answer here is basically saying the hydronium ion concentration is being increased by a factor of 1,000.
Wow.
In that case, it would be decreasing by a factor of 1,000. So we're gonna you instead of using like negatives, I would say it's better to say, and I'll write this, increasing by a factor of 1,000. Cool. It is. So again, I'll be even more specific with the writing. I'll say the hydronium ion concentration, the H3O plus, is increasing by a factor of 1,000. So you're right. It is getting more acidic because we're going down on the pH scale, meaning even though we're going down in number, that means that we're actually increasing the amount of this stuff.
So for our answer, we just write increase by.
Yeah, increase by 1,000. I would guess if he gave you something like this, there would be like increase by 1,000, decrease by 1,000, increase by like 10, or maybe it would say increase by 3, decrease by 3, increase by 1,000, decrease by 1,000. Those would be some good like wrong answers that would be tricky. So I have a few more examples of this though, so let's do it. If the pOH went from 5 to 9, by what factor would the hydroxide ion concentration get impacted? Again, I said this in the last session. When I see pOH, my brain kind of freezes. I can't break down what that means in terms of acidity or basicity unless I really think about it. So I always immediately flip it to pH. So if we're going from 5 to 9 on the pH scale, think about it as going from 9 to 5 on the pH scale. Did I say that right? Keep saying pOH, pH. If we're going from 5 to 9 on the pOH scale, that's the same as saying we're going from 9 to 5 on the pH scale, and that makes more sense to me. See if you can figure this answer out, though. So are we getting more acidic or more basic? We're getting more acidic on this one. So again, there's different ways to think about this, but if I see pOH scale is going from 5 to 9, I'm going to make it more simple in my mind and say that the pH scale is saying that this is going from 9 to 5. That's the same thing. And to me, 9 to 5 makes a lot more sense. If we're going from 9 to 5 on the pH scale, that's acidic, right? The lower you get, the more acidic you are. So we're getting acidic. We know that. So would the hydroxide ion concentration be increasing or decreasing? Decreasing. Yep. We have to be very careful with like, there's a lot of little spots where the wording can throw you off. So again, hydroxide ion is the OH minus. If we're getting more acidic, this is going to be going down. So it's going to be decreasing by a factor. Now we need to see what that factor is. And there's 4 values between 9 to 5, 5 to 9, whatever. So 10 to the power of 4 is 10,000. So the answer to this one is we are decreasing our hydroxide ion concentration by a factor of 10,000.
Hydroxide basic. Right?
Basic.
Hydrogen is
Exactly. Yep. And again, this is one of those things that is tricky. I mean, it's like very easy for the wording to throw you off. So the more practice you get with it, the better. So I'll do one more. We have this time it's like multiple choice. I'm saying which of the following shows a pH change where the hydroxide ion concentration increases by 100,000. So again, let's break down every part of that. We're dealing with hydroxide ions, so we're talking about basic. And we're being asked to find an area where it is getting more basic because we're increasing hydroxide ion. And specifically, we're getting more basic by a factor of 100,000. And we're doing pH scale. So first off, we know if we're getting more basic, it has to be, and we're using the pH scale, has to be going from a smaller number to a bigger number, right? So right off the bat, we can get rid of 2, 3, and 4. I think I didn't give the best options here, but we can get rid of all 3 of these ones here because they are all instances of something getting more acidic. So we know already the answer is going to be 1. It's going to be going from 4 to 9, but let's also make sure we understand why. So if we're going from 4 to 9, that is 5 values in between. We'd say again, 10 to the power of 5. And you can type this into your calculator if you need to, of course. It's 100,000. So we're good there. And we're getting more basic. And so we're getting more basic by a factor of 100,000. And we're specifically, we could say increasing hydroxide ions by that factor. Do we feel good with that stuff? Cool. All right, next one. Now, this is a better example of the type of thing you were doing on Friday. So we have a pKa given for a solution. It says its pKa is 4.05. And the initial concentration of CH3CO2H in a prepared solution is 0.20 molarity. So if you see this molecule here and you're like, well, I don't know if that's an acid or a base, totally fair. I mean, we should be at the point, hopefully by the time of the exam, where you could see this and kind of predict that it would be an acid. But that is some like a little bit higher up chemistry knowledge. So this is something called a carboxylic acid. This is what this molecule looks like. We have the CH3, CO, so the 2 O's, and then an H. And for anyone going on to Orgo or biochem, especially both of those classes, carboxylic acids are like really one of the most common acids that we see in the human body. So they're very important. But we're also told we have a pKa and it's 4.05. pKa's are representing the K dissociation constant for an acid. But it's a pKa, so it's not the same as a Ka. The way to go from a pKa to a Ka is this. pKa is equal to negative log of the Ka. And the way to go from Ka to pKa is 10 to the power of negative Ka. Sorry. 10 to the power of negative pKa. That's right, is our Ka. Make sure you do that in your calculator. First things first, we want to make sure we have a Ka value instead of a pKa. And then I'm asking you to kind of break down step by step the process of how we would find out what the pH is for this solution. So we do need to do an ice table for this. And again, we said that if it's a strong acid or a strong base, like we did at the very beginning, you don't need to do an ice table. You can kind of skip that part when it is a weak acid or a weak base. And, CH3CO2H is not one of those strong acids you memorize. So we know it's not strong. That's when we have to do a whole ice table. So spend a few minutes working on this. If you get stuck, don't worry about it. But I'll go over the work up here. All right, we can go over this. I didn't finish it. I'm going to kind of work through some of this with you guys. That's better. So here's the ice table setup. Again, we always do the reaction, then the initial, the change, and then equilibrium. That part's review. We're going to start with the acid here, and we know that we're always reacting an acid or the base with water, but water doesn't really count for the ice table. We're forming the conjugate base and then the hydronium ions. That's why the water matters, is because we need it to form the hydronium ions. And so we are told we're starting with 0.20 molarity. Again, your ice tables always need to be molarity. That won't really be an issue yet, but when you get to the next unit after spring break, you're gonna have to do some stuff where you do a thing first where it's not molarity, then turn it to molarity, and then do your ice table. So ice tables are always molarity. We do minus x, plus x, and then we can set up the Ka expression. Again, dissociation constant is always products of reactants. So I guess for part B, I want you to write that. So let's do that real quick. Ka looks like this. It's always going to be in the numerator, your conjugate base and the hydronium ions. This is for every weak acid. This is what their Ka is going to look like over the weak acid itself. So we're good with that. That part's review. Again, water doesn't go into it because it's a liquid. And then what's the next step here? So we've found the Ka. Again, we did 10 to the minus pKa. What can we do to find X?
Uh, something I remember he's like you can get rid of the X,
Mhm.
it's dominating. Like that's like if the number is big enough,
If the number's small enough.
well,
Yeah, so you got it. So there's two different ways to solve ice tables that he'll give you because he doesn't want you to do quadratic equation, the quadratic formula. And so what we do here is when we see that it's something like 10 to the minus 3, 10 to the minus 4, anything smaller than 10 to the minus 3, that's kind of my number that I go with. We can get rid of any instance where we're adding or subtracting x. We can't get rid of this because x is the term, but we can get rid of the minus x. So then we can do this in our calculator, multiply by the denominator on both sides, and then take the square root of both sides. Again, the way I do the square root is, so I multiply it by the denominator, then I'm going to do raised in parentheses 1 over 2. That's my way of doing it. And so we get x as being equal to 4.22 times 10 to the minus 3. And this is not the answer. It could be a fake answer that he puts on the test, so you got to be careful. Because we're asked to find, this is extra tricky, we're asked to find the POH. So we're going to need to do a couple steps. But we know that x is equal to hydronium ions at equilibrium. So we can do the minus log of this, minus log of x. To get a pH. Our pH is 2.37. But again, that's not enough. I made this one extra tricky, so we need to find the POH. So we're going to do 14 minus that. And find that the POH is 11.63.
Yeah.
Yeah.
How you do?
This to this.
No, I have the X value.
Uh-huh.
How do you get the?
pH to POH. So the POH is going to be always, I'll write this up here. POH is 14 minus the pH. So I did 14 minus 2.37.
No, how do you?
Oh, good question. Since we know that we found x, right? That was the whole point of doing this k expression thing. X is right there. This is really the big thing we're always looking for in one of these ice tables, because this is the equilibrium concentration of hydronium ions. So all we have to do is take the negative log of x to find pH, because taking the negative log of x is the same as taking the negative log of the hydronium ion concentration. So I did negative log of this value. And then again, we always want to make sure, does it make sense, these values that we got? pH of 2.37, is that, maybe something we could expect here? Yeah, the answer is yes, because first off, we have a pKa value that's kind of low. That's one of the clearest indicators, but we're also doing a ice table for a weak acid. So if we're ever doing an acid ice table, we should expect that the pH is slightly acidic. So it's a good way to make sure we did everything right. All right, next one. This one is one of my favorite problems to talk about in the semester, because this was on one of my organic chemistry exams and I got it wrong. Oh yeah, I guess I skipped that part. Good call. To determine yeah, you could do that. We could also use KW. I mean, it's kind of, you can imply that we're at 25 degrees Celsius. So we could use the KW, doing the like 1 times 10 minus 14 divided by the hydronium ion concentration.
Could you also?
Yeah, you could. Both of those would work. Good question. All right. So yeah, this one here was on my organic chemistry exam and I got it wrong. And using the knowledge that you guys now have, you could get this one right. The only difference was on the exam, we weren't told the pKa, so we had to, once you get to Oreo, you have to be able to kind of determine how acidic something is based only on the structure, but we're not there yet. So I gave you the pKa's, and you can also infer that B is wrong. This is not right. But let's talk about this one. I'm not going to have you guys solve it on your own because this is a little tricky, but you should have all the info needed. So we have an equilibrium reaction where we have, says isopropyl SH. That's what the IPR is. Kind of looks like this. Again, you don't need to know any of this stuff, but plus ETONA, that looks like this. ONA. This is an ethyl group. We're at equilibrium, and we have isopropyl SNA plus ETOH. So it's going to be like this, OH. So this is a basic, like a standard acid-base problem where we're at equilibrium. We can tell that this is going to be the acid on this side. So this is an acid, and this is its conjugate base. And then over here, this guy is also an acid, and this is its conjugate base. The way I can tell is because the only difference is over here we have a extra proton, and it's donated the proton and replaced it with a sodium. So the sodium is something called a counter ion. It's basically there to keep the thing balanced, but we're not worried about the sodium. All that we care about is that this thing donated a proton and became a base. This guy over here, same deal, donated a proton, became a base. That should be not too bad yet. Now we're given pKa values. So I'm telling you that ETOH has a pKa of 15.9. So again, that's this one. So this is pKa of 15.9. And isopropyl thiol has a pKa of 10.86. So now we need to think about what does that mean? Is a higher pKa or a lower pKa indicative of a stronger acid? Lower. The lower the pKa, the stronger the acid, exactly. So we can say this guy is a bit of a stronger acid, right? So now we need to tell where equilibrium is going to lie. And this was like the last problem on your active from Friday. It was kind of like this. We said that the site of a stronger acid is going to favor that forward reaction. So we said that this is the stronger acid. I'm going to write stronger, which means that we're going to be really favoring this reaction, going towards the product. All you need to know there is that the thing is a stronger acid, so it's better at donating the proton. It's better at kind of getting its job done. You can think of it that way. So if we know we have more products at equilibrium, that kind of gets to the question of where would K equilibrium be? Would it be less than 0? Would it be equal to 1? Or would it be greater than 1? It'd be greater than 1. Yep, because we're favoring products. So if we have a lot of products at equilibrium, K, again, is always products over reactants. So if we have a lot more of these, this is going to be greater than 1. So I think that's kind of cool. You guys can now do kind of an orgo problem. But do we feel good about the parts that are important for you guys to know is that a lower pKa means a stronger acid, and it favors the side of the stronger acid reacting. So Ka is the opposite. The greater the Ka, the stronger the acid. So Ka is like, that's a great question, actually. So K is, if it's greater than 1, that's the same way as us saying like it's strong, it's a big number. Whereas pKa, since it's this tricky like logarithmic thing that I don't fully understand, but basically pKa, you want a smaller one for a strong acid, and at Ka, you want a greater one. This is the last thing I'll say about this because I don't want to confuse anyone, but we know that if a Ka value was like 100,000 or something, like a really big number, that tells us it's really product favored, right? So that lets us know that we're like reacting pretty well. We're going to the product side very well. So think of it that way. Like you want a big Ka because that shows that we're going to the products faster. But a pKa, I would simply memorize that the smaller one means more acidic. Like that. The next problem. Greater the Ka, the stronger the acid strength is. I don't know if that was a statement or true or false or something, but that's true. So good thing to remember.
No, K bigger is more important.
Yeah, I can just write this out. Lower pKa, stronger acid, higher Ka, stronger acid. And we favor the side of the reaction where the stronger acid's reacting away. Okay, last one I have, another one of these weak acid, weak base problems where we have a K value given, and I'm asking you to do an ice table to solve for it. I want to make it a small adjustment to this one because on Friday he said that if he ever gives you a Ka, assume it's an acid. If he gives you a Kb, assume it's a base. Um, I guess that's what he's doing now. It used to be where sometimes you would be given a Kb, but you need to turn it into a Ka. So real quick, let's go over this. Kw is equal to Ka times Kb. So this thing, I mean, the word acid is in its name. Hydrocyanic acid is an acid. So we don't want to use Kb. So let's turn it into Ka from Kb. So we know Kw is 1 times 10 to the minus 14. If we divide by Kb, that can get us Ka. So let's do that right off the bat.
We don't make sense, we're gonna do that.
No, based on what he said on Friday, he said if he gives you a Ka, that's an acid. If he gives you a Kb, that's a base.
Is that-
Yeah.
Do you think like we really need to focus on like memorizing them?
Memorizing like all the weak acids and weak bases. No. Yeah. Yeah, the question itself, the wording and stuff should kind of tell you, are we dealing with an acid or a base? Like I said on Wednesday, you do get a little bit into being able to tell if something's a stronger acid based on its structure, but there's no way he expects you to memorize like every acid and base in the world because I mean, almost everything could be considered an acid or a base. Um, so yeah. Uh, if it's not in the PowerPoint slides, don't go past that detail. And I would say a lot of times you can kind of tell if something's going to be an acid based on is there an H available? So like up here on this one, again, this is something that you had never seen, the CH3CO2H, but we have a little proton floating on the end there. So it's kind of safe to assume this could be donated as an acid and it would form its conjugate base where it has a minus instead of the proton. So yeah, now that we did an example all the way through, see if you guys can do this one by yourself. Again, here's the Ka, so use this when you're doing your ice table. Let's work through this one. So again, we have HCN. He might give you the name itself, he might not, but that is hydrocyanic acid. It's not one of those strong acids. We know it's a weak acid. It's at equilibrium. And so it's going to be producing its conjugate base, and that's going to be CN with a minus, plus the H3O plus. That's what we really care about here. So the ICE, we're starting with 0.062 over here. Get rid of water, nothing, about nothing, minus X, plus X, plus X. 0.62 minus X, X, X. And again, we have a Ka value that we're going to use. You'd get the wrong answer if you used a Kb. So that's a very important thing to make sure of. It's going to be X squared over 0.062 minus X. And then again, we can do that approximation since it's times 10 to the minus 5. That's about small enough. So that's the trick here. We got to get rid of that guy. And now we can multiply by the denominator on both sides. And take the square root afterwards and find that X is 1.12 times 10 to the minus 3. And that means that it is our hydronium ion concentration. That's what we're looking for. That's kind of how we get an answer in the end. And so we know that if we have the hydronium ion concentration, you can do a negative log of that value to get the pH. Oh, you did? As long as everything else is right, you got the process down.
Yeah, I think I did the problem right.
So are you difficult by the 0.06?
Yeah. Yeah. So I multiplied both sides by 0.062. That kind of gets rid of that denominator. And then I would take the square root of this to cancel out that exponent there. And again, so the pH is going to be 2.95, meaning that the pOH, if he asked for that, he probably would ask for the pH, but it's good to always do this review. It's 14 minus, so that's going to be what, 11 05? Yeah. Cool. So pH pretty low, tells us that we're dealing with an acidic solution. But we already should know that, right? Because we're dealing with hydrocyanic acid. But this is the big process that he taught about on Friday. You'll get a little bit more info tomorrow. I don't know exactly what he's going to be teaching, but I'll do a full test review on Thursday so we can go over a lot more practice like this.
So you are doing the review on